Good afternoon, everyone. Thank you very much for joining this final presentation of the AI for Health team from Fruitpunch AI. So my name is Jennifer Dont. As Bram mentioned, I work at Mastro, and I had the great pleasure of guiding this team over the last few months. Although when I say guiding, it's kind of an overstatement. To be honest, I didn't really have to do much in the last few months, except sitting in on a meeting every 2 weeks where they showed their progress and their results. And I just had to say, well, that's really well done. So just to give you a bit of background, this project actually started already, not the project itself, but the idea in October, quite some time ago. I had to check my emails if that was correct, but at that time we received an email from Bram in our research group saying that they had some interested students who wanted to do an AI health-related project. And we could basically do some propositions. And looking back, I was very lucky that they chose one of my projects at that time, which wasn't the project that they will present today. It was a project related to energy conversion, also with deep learning, but something completely different. Unfortunately, I think on the day that they were planning to start, although all the administrative work was finished, we actually didn't have a single image to work on, which sometimes happens with AI projects. But luckily, we also had some other issues lying around, some other data that they could work on. And I have to say they were super professional and they just immediately switched to a topic they didn't initially choose, but in the end, I think turned out really, really well. And I'm also very happy to see the results today and that they can present them to you. So I give the floor to the students who did basically all the work over the last few months.
Thank you for the kind words, Jennifer. Good afternoon, everyone. Thank you all for showing interest in our Fruitpunch AI for Health project, covering to improve the automatic lung segmentations from X-ray images with the use of a generative adversarial network. My name is Myrthe van den Berg, and together with Jans van der Zanden, I will present and discuss our methods and results. This AI for Health project is initiated by Mastro and aimed to optimize the current workflow of the radiology department at the Maastricht Universitair Medisch Centrum. This project fits the Fruitpunch AI mindset, as Fruitpunch aims to implement innovative solutions for complex issues affecting society. First of all, I would like to introduce you to our team. This team consists out of students from data science, AI, and medical engineering. A quick side note, this picture was taken during the only time we've been together as a team, but working online did not limit us during this project, and we were able to produce some promising results that we will gladly show you today. Now back to the project. The main goal of this project was to build a generative adversarial network that accurately segments the lungs in chest X-rays. This network will be employed in a bigger and improved workflow regarding COVID-19 classification. The current workflow involves 2 time points where a radiologist has to examine a patient, which is first to detect if there is a COVID infection, and in the later step, it's to further specify the severity of the infection. And you can imagine that this is a very time-consuming task to do manually, especially when there is a huge influx of patients that we've seen this past year with the COVID infection. And this can slow down the general care process, which is unwanted. And a way to support this process is to create a neural network that can help classifying these images and assist the radiologist in making their decision. And for this, the segmentation of the lungs is the first step for training this classifier on lung diseases such as COVID-19. This ensures that the classifier is exclusively trained on lung tissue and does not get any features or other unwanted items from the image other than the lung. However, this is a challenging task, as due to the severity of the infections, the lungs are less clearly defined on the chest X-ray image. This is why conventional segmentation models usually fail, and it is expected that a generative adversarial network would perform better. Generative adversarial network can be summarized into 2 simultaneously trained neural networks, a generator and a discriminator. And in our case, we were working with the conditional generative adversarial network, which means that the input of the generator is an input image instead of some random noise. The generator is usually a known segmentation network that produces the masks, whereas a discriminator is a classification model that predicts whether a mask is true or generated by the generator. This has the added benefit of a check to see if the generated mask is looking like a real mask. The goal of the generator is to fool the discriminator. Therefore, they are in some kind of competition, and the goal during training is to find the equilibrium between these 2 networks. Before delving into the specifics of these models, I will first elaborate a bit more on the dataset itself. The dataset we've used for this study is a combination of 4 open source datasets of patients with either a form of pneumonia or COVID-19. In total, these sets added up to approximately 1,000 2D chest X-ray images, and From these images, we used 80% for training, 10% for validation, and 10% for testing. Some datasets provided ground truth masks. The masks included in the dataset had to satisfy a number of criteria. The most important one is that all masks needed to have smooth edges and follow the contour of the lungs closely, which you can see on these images on the right on this slide. For 2 datasets, we had to manually draw our own masks, as one did not comply with our criteria, and another dataset, the COVID dataset, did not provide us with any ground truth masks. And since the team is not specialized in this task, we consulted Mastro in some challenging cases. As we used 4 different datasets, it was important to apply some pre-processing. One dataset was characterized by having large areas of zero padding, which you can see on the right side. We removed these areas as they could affect the next 2 steps in the pre-processing. We standardized the images by their own mean and standard deviation in pixel values. If these black areas were still present, this would affect these statistics of the image negatively. Thereafter, we resized the images by setting the largest axis to 512 pixels and add zero padding to the other axis to make the images squared if needed. The difference between not removing the black areas and how we did it is visible in these images on the slide. Traced with pink, you can see in the top image the original image in the dataset, and in below you can find the image after we pre-processed it in our way that I just described. And you can see that the image to background ratio is higher, which is beneficial during training. Now that you have a bit of an idea about our input data, let's discuss the model architectures a little bit more. You might recall this schematic from an earlier slide, but I will now explain the training process more thoroughly. To update the weights from the GAN, first the discriminator is trained on the set of real examples, which is the random input image with the real mask, and then the weights of the discriminator are updated accordingly. Thereafter, the discriminator model is trained with the input image and the generated mask by the generator. And then the discriminator has updated its weights accordingly to that training process. And then the discriminator is frozen during the weights of the discriminator are frozen during training so that the generator can be trained. This uses the input from the output of the discriminator model and uses the input image and the true mask to further optimize that model. Once the cycle completes, the weights of the discriminator are unfrozen again and the training starts with a new set of images. When zooming in into the generator, it consists of an encoder and decoder block combined into a UNet architecture. This UNet model first passes the input into the downsampling layers, which is the encoder side, until it reaches the bottleneck. Here the model is forced to learn a compressed view of the features of the image. Then this bottleneck representation is passed into the decoder set of the decoder layers from the model. There are skip connections you can see here on the bottom that help the model learn more fundamental features such as the lung edges, and these are passed from the encoder layers to the decoder layers directly in the corresponding level. To be more specific, the model is built from 7 encoder and 7 decoder blocks, and every encoder block consists of a convolutional layer, conditional batch normalization, and a leaky ReLU activation. It downsamples the input and passes this through, and the decoder block upsamples the input from the bottleneck. The first part of the decoder consists of a convolutional transpose layer, a batch normalization, and a conditional dropout. And then it takes the input and concatenates it with the skip connections from the encoder. Those are the skip connections I mentioned earlier. And they also are followed with a leaky ReLU activation. When the input is pressed through all blocks, it is transposed one last time before it encounters the sigmoid activation, which produces the output. And this output represents the chance for every pixel to be lung tissue or not. And we put the threshold on 0.5 to binarize the mask. The generator is optimized with the Atom optimizer, and therefore we used a weighted combination of the binary cross entropy, which is outputted from the discriminator model, and the mean squared error, which is the error that's computed from the output mask and the ground truth mask. The discriminator is a convolutional neural network with a little less complicated structure. It's built up from 6 convolutional layers, and as input it takes the input image and the mask that's either generated from the generator or is the ground truth mask, and it tries to predict if the input mask is the real mask for the input image or a fake mask generated by the generator. The structure of the model is that when the input is concatenated, it passes through the first convolutional layer also with the leaky ReLU activation, and this step is followed by 5 more layers of convolution, batch normalization, and leaky ReLU activation. Finally, a sigmoid activation is used to classify the input mask and test the prediction if it's a real mask or a fake mask. To optimize the performance, the Adam optimizer with the binary cross-entropy loss function was used. As the loss functions of the discriminator and generator fluctuate a lot during training due to their competitive nature, we have added a validation loss framework as shown on the slide so that we can keep track of model convergence. This validation loss is defined as a negative die-score so that the loss would keep decreasing, and that is more intuitive to make sure that the model is still going the right way. And Jans will further elaborate on the die-score when explaining the evaluation measures on the test set. And when the validation loss did not decrease for 5 times in a row, the training process was stopped to prevent overfitting, and the generator model weights were saved every time that an epoch resulted in the lowest validation loss thus far. In an attempt to improve our results, we also tried to increase our dataset with the use of data augmentation. And this entailed that for one original image, an augmented image was created. And this is done by generating a random value that picks a degree of rotation, translation, and the variability of the Gaussian noise. And this range of values for the rotation was between -15 and 15 degrees. The range for translation was between 0.05 and 0.15. And for the Gaussian noise, we used variability of 30. All in all, this step doubled our dataset. However, since our code used an array that loaded the entire training dataset before entering a training loop, increasing the dataset like this on the original 512 by 512 size was not possible with our GPU resources. So we tried downsampling the images to half a size, and this was feasible, but eventually this led to worse results than the original dataset in full size. So therefore, the results we will show you today are on the dataset without data augmentation. And I will now give the floor to Jans to talk more about our post-processing of the generated masks and an analysis of our results.
All right, thank you, Myrthe. So while analyzing the results after training, we saw some inconsistencies in the generated masks. In the example on the left, you see some separated white areas that do not represent lung tissue, and other masks included some small black holes in lung tissue. So to overcome this problem, we used morphological operations. So we started with the opening with a kernel size of 5 by 5, and that was followed by morphological closing with a kernel size of 4 by 4. So it did affect the mask with poor quality, and it didn't not greatly affect mask with higher die scores. And for evaluation, we decided to implement 2 metrics as they assess different aspects of evaluation on the test set. The die score as an overlap-based metric and the Hausdorff distance as a distance-based metric. So as Myrthe mentioned before, she mentioned the die score. So what is this die score? This die score is a coefficient that measures the similarity between 2 sets of pixels and is calculated by 2 times the area of overlap divided by the sum of the 2 sets of pixels. And as an addition to the evaluation of the generated mask, we also calculated the Hausdorff distance. And this Hausdorff distance defines the maximum distance between 2 sets of pixels. In this case, we used the ground truth mask and the generated mask, and then it calculated the max distance between those 2 masks. And then here are some plots about the results for model convergence. As you can see on the first image on the left, the training process of an generative adversarial network is very unstable. As you can see on the dice loss, at every step, it's very fluctuating. In the second plot, you can see the mean dice loss for every epoch, and eventually leaving us with a test loss equal to minus 0.94 and the Hausdorff distance of 30.2 pixels. We also checked the model performance with different random seeds, and this resulted in a die score of, or a mean die score of 0.93 with a standard deviation of 0.001 and the Hausdorff distance of 30.2 with the deviation of 2.75 pixels. And this is shown with these box plots. The test set consisted of 99 generated masks for each trained model. As you can see, the die scores indicate that the models perform equally well, whereas the Hausdorff distance values show a broader spread and more outliers. The mean test Hausdorff distance values are approximately the same, and they also checked the performance with different train and validation splits. And the model performance can be qualified by a die score of 0.95 and with a standard deviation of 0.002. And the Hausdorff distance for these models was equal to 29.72 with a deviation of 1.84 pixels, also visualized with these box plots. In these box plots show that regarding the die-score, the models seem to perform equally well. The variation between the different test scans is smaller than looking at the different model initializations. The lowest die-score is around 0.65 and it's seen for one prediction made by model 5. Regarding the Hausdorff distance, one could notice more differences between the trained models. Model 4 shows the lowest mean value while having the most outliers. And here are some results of our visual inspection. On the left side, you see some generated masks with a higher die-score, and they look very similar to the ground truth masks. And on the right, you see two examples with a low die-score. The first example is understandable to have a low die-score, since the borders of the lung tissue are not very clear. And for the second example at the bottom, the lines are clear, but the algorithm is not capable of generating a desired mask. We also have here 3 examples of the inter-observer variability. And this is all team members have drawn mask manually. And the pink squares show some important differences. For instance, in the left picture, there you see on the right lung, different members of the team have drawn the aortic arch differently. And for example, here, some included the heart. And at the bottom of the images, you can see the corresponding die-scores. These die-scores are the mean and standard deviation of all possible 10 combinations of team members. And these results are in line with the results of our trained model. So as you can see in these images, some of our data set included some masks that contour masks that were not drawn correctly. This is a limitation of our study. Since these masks were drawn correctly, then the heart wasn't segmented as lung tissue, and our model does not include the heart tissue. So that would result in a higher die-score. And also our data augmentation was applied with images of 256 by 256, and therefore there's information lost since we used images of 512 by 512. So for future studies, it's widely known that deep learning models such as GANs are very data-consuming algorithms and need large amounts of training data. So adding more data for our training process would be beneficial. Also, testing the model on a completely new data set will give insights about the generalization of the model. And furthermore, future studies could also do more extensive data augmentation. Our code had just one augmentation, which is an image with rotation, translation, and noise. It's also possible to do, for instance, augment an image 5 times based on one image with different values for rotation, translation, and noise. And that brings us to the conclusion. Although the best performance of our GAN seems to outperform a unit on the same task, it needs to be considered that with more parameter tuning of the units, similar results should be in reach. It is, however, interesting to see that our model scores higher than our own inter-observer variability. This gives rise to the question, how much better can the model possibly get? And to answer the question, an inter-observer variability check should be done with the real radiologist and that segmented the trained data, and this would give a good baseline for our models to strive to. This can possibly be a suited tool for future clinical implications. Unfortunately, we did not have the chance to train our model on large quantities of data. Our expectation is that by increasing the data set and the quality of our data, our model will increase in performance. And for now, it would be irresponsible to imply the actual clinical value of this model. And for the parameter tuning of our model, we found that only the batch size and loss function caused noteworthy changes. Also, experiments with the data augmentation suggest that a larger data set would result in a higher performance on unseen data. So we've come to an end of the presentation. We would like to thank Mastro and Fruitpunch AI for this fun and interesting challenge. And thank you for your attention.